Recorded is rolling. It is Wednesday, December 7th. So I want to hit one college fitness problem with you guys real fast.
Good morning, VR High School. My name is Tristan Shoemaker, and today is the 81st anniversary of Pearl Harbor. We must remember that through the darkness that occurred that day, we were able to find a light. It still holds true today. Make this day count, Sierra.
Our main thing is going to be AP Classroom Unit 7. Go over those with you guys. You guys know there's a rotational dynamics quiz tomorrow. You guys know this is open notes, right? Open notes. No, guys, open notes. You guys are still going to study, right? You're going to study because there's some really challenging questions because you don't want to go into questions like, oh yeah, wait, I do kind of remember seeing that. If you study ahead of time, then when you see some really challenging questions, you'll be like, oh yeah, I know like kind of how to navigate this, right? I'll pick up you guys' puzzles tomorrow. You guys can turn this in with the quiz. You guys can use those with the quiz if you want. It can be part of your open notes. We'll start the midterm on Friday. Okay, so just what I want to hit because I've explicitly covered all the ones I assigned you guys except for this one. So I want at least mention this. So there's this, let's just call it an air hockey puck. So there's like zero friction. It's going around, shoo, shoo, shoo. And there's this guy pulling on a string through a hole in the table. You guys see that? Okay. And this guy's going to pull down. And then when he does that, the radius of this motion is going to decrease, kind of, it's going to like move in, right? Okay. Now, if you point a radar gun at that puck, do you think the linear speed of that puck is going to increase as it's going in? I think it probably would. It kind of makes sense, right? And that's the well, the question is like how much work is done like pulling it down. Now maybe they could have asked different questions or phrased a different way or framed it different ways. But if you saw anything kind of like this, one thing you'd have to, regardless of what question they ask, you have to think, well, what framework would I have to use to solve this? And sometimes there are multiple ways to go about solving things. But would you want to use conservation of energy? Conservation of energy. Okay. How many guys say no? That would be a bad way to do this one. Okay. If you're saying no, then that is correct because do you guys think it takes some effort to like pull down? Do you think he's applying a force for some distance? In a sense, he's like putting work into the system, putting energy into the system. That's why you would not want to use conservation of energy because this would be like an open system, wouldn't it? Right? The amount of mechanical energy from beginning to end is going to change. Right? Is it going to increase or decrease? It's going to increase because he's like pulling. Right? He's putting work into the system. Right? So they said how much work was done. Hint: consider the kinetic energy of the puck. So well, you could sort of use energy, but it'd be like as an open system. So the initial energy plus the work done equals the final mechanical energy. Okay? But really, the setup I'm going to do is conservation of momentum, conservation of angular momentum. I'm going to treat this a lot like the ice skater. Okay, you guys remember? Okay, show you guys this picture again. You guys remember the ice skater? Momentum is conserved. Okay, angular momentum, I times omega is conserved. Okay. Right, so if you start from that, okay, then you can do some substitutions and you get an expression that looks like this, which, could you kind of treat the hockey puck like a point mass? And look at this, MVR, if you rearrange that, MRV is the same thing as MVR. Hey, didn't I also tell you guys that angular momentum for a single point mass is MVR, right? There, like 95% chance you guys are gonna see something like this on the AP exam in May. Okay? You throw a point mass at like a swivel stick, right? And then once it collides, it like sets this whole thing in motion, I times omega. But what is that I times omega equal to? Well, I bet it's equal to MVR, like the source of the angular momentum to start with. This mass times this speed times, the radius of curvature here, that's like pivoting around this point, right? Okay. So same idea here. That's what it boils down to. Right. So you can solve for the post-collision velocity. Okay. You know what it was, pre-collision, you got a post-collision, and they say, okay, well, what's the work done? I've got an open system right here, right? The work done is the difference, final minus initial kinetic energy. Okay, then you go solve for it, blah, 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 and get the answer that way. Right. There's some conversions in here like prefixes and like that. Right. It's little details. Right. Right. So you guys go there? All right. Let's see. I'm gonna flip the screen over here. Let's flip the screen. All right. Let's take a look at AP Classroom. Unit 7. Right. One thing right before I get to that, I just got this flyer in my inbox that next week is a Spirit Week. I did just post this to Google Classroom. Okay. So what we got? Monday is hats and socks. Tuesday is I guess sweaters, ugly sweaters. Wednesday, we got Santa versus Grinch. We're either green or red. Thursday, holiday character day, and Friday is holiday. Oh, PJ. Oh, PJ day. All right. So it's not hard. All right. So let's do AB classroom.